Okay, sorry that I'm not be able to in the class because I'm in the conference. So this is the Advanced Computer Vision CIP 6412, and this class I'm the instructor, and this is my email address, and my office is upstairs on second floor 245. It's phone number, and these are the office hours, and this is the time of the class, 3 to 4:15. Tuesday is a Thursday, and HEC 117, you are in this room, and these are the office hours. On Tuesday is right after the class, and then Thursday 2 to 3 p.m. and by appointment. We have additional hour, which will be discussion session Wednesday 3 to 4 p.m. will be in different room, 356. And this is the hour we will have some time. Students may have questions about a particular paper, then we will organize a session that can provide you additional help. And there'll be some other presentation, I'm going to talk about that. So prerequisite for this class is 50/15, the computer vision. And this is the course web page. So the objective of this course are that the graduate students will be exposed to the cutting edge research. In each class we'll discuss one recent paper which related to computer vision, the current research area, and in particular implying deep learning. So outcomes of students will be that you will learn how to read and understand the research paper, write a comprehensive review of the paper, and identify strong and weak points of a paper, and to come up with your own ideas to solve same problem, which may lead to your own paper. And also there'll be some programming assignment or the project that will give you experience implementing some of these papers, or get an individual project which you have to complete successfully. So grading will depend on the reports and the presentation and the attendance discussion and the programs and projects. So this is a late policy. So since we are going to use deep learning, so you will be needing implying GPUs, which many of students don't have GPUs. So we will provide accounts at the UCF high performance computing cluster, and that will require some experience in Linux. And each student will get an account. There'll be a presentation about how to use the system on Wednesday next week, 3 p.m. This is a discussion session. I mentioned earlier in 356. Of course, if you have own access of GPUs yourself, you don't have to get the account. But in general, most of the students don't have the GPUs, so this is first time you are providing the account so that you can train the system with more data and so on. Otherwise, it's going to take you a long time on CPU. So we'll discuss papers, one paper in each class, and each student will have to make a presentation. You have to select one paper. We'll see how it goes. Each student may have to select 2 papers, and these papers are provided in a list on the course web page. I'll show you that. And so you can select paper from that and let me know when you want to do it. Or you can suggest, paper yourself if you are interested in a particular paper and get my approval, then you can do that also. These papers have to be related to computer vision, deep learning, and in the major conferences. All students will read the assigned paper before the class and write a report. And reports will be due before the class meeting through the web courses. And one student will be responsible to present the paper, and then this presentation will be 30 minutes. After that, we'll have discussions. So the reports should be one page, not more than one page. It should have following sections: brief summary of what is the paper about, good points you like about the paper, weak points, and the questions you have which you didn't understand, and some ideas you get after you read a paper. So this is the schedule for the paper presentation. So the PowerPoint presentation you will prepare will be reviewed by me. If you are presenting a paper on Thursday, then you will come to my office at 2:30 on Monday to show me your presentation. I'll give you comments how to improve, and then you will do the rehearsal for the presentation on Tuesday during the office hours, 4:15 to 5 p.m. and this will be in my office. So that's the schedule for the Thursday if you're presenting paper on Thursday. If you're presenting paper on Tuesday, then the review of your presentation will be a week before on the Thursday during the office hours, which is 2 to 3. And then rehearsal will be a Monday during the week that you will present your paper. So that will be at 2 p.m. So you guys already know about the statement of academic integrity, and we will follow that, and no cheating or any plagiarisms allowed. You will automatically get the F. So that there's no textbook. This is an advanced computer vision class, so it's mostly we'll discuss the papers. But if you want to learn more about the deep learning, there's a very nice book which is actually available for free by Goodfellow. You can get that electronic version. And we also have different resources because we did this class last year. So if you don't know deep learning programming, then we have a nice tutorial on this URL by one of the graduate students. And then we have also a tutorial on introduction on deep learning, which my postdoc and myself did. And these are the YouTube videos. You can watch these presentations. And then, of course, you can look at the website for the last year class, which is even here. So these were the different papers we did. And for each of the paper, we have video. So this is a Keras tutorial I mentioned. So you can click here. You can get a track video, a YouTube video of that. And these are the different papers. For each paper, we have a presentation, PDF, and the video. So that should be pretty useful. So going back to the this year, so besides that, there are lots of online courses and tutorials on deep learning and computer vision and so on. This is the most popular, Andrew Ng from Stanford University, and many more you can always refer to. And these are the dynamic times where more resources are being put online, which you can benefit from. So let me give you some idea how you should read a paper, a research paper. First is that you have to read a paper several times to understand it. And when you read the paper first time, if you don't understand something, don't get stuck. Keep reading, assuming you will figure out that later. When you read it second time, you will understand much more and third time even more. So that is one important point, that you cannot just, it's not like a fiction or history or something you just read once. Research papers are involved, so you have to read several times. Also, the idea should be to try to get a general idea of the paper the first time when you read. So you can ask these questions: what the problem is being solved, what are the main steps, how can I implement the method, because computer vision, all the methods you can implement and get the results, and that will help you to understand the paper. And then try to relate the paper to other methods, other papers conceptually, and find similarities and differences, and that always helpful. In the first reading, it may be a good idea to skip the related work because you don't know the particular area, so you want to just focus on the paper you're reading. And don't use dictionary to just look up the meaning of technical terms. Then try to understand each concept in isolation and then integrate them to understand the whole paper. So the time we are living, it is very disruptive time because deep learning has impacted lots of areas, including computer vision, machine learning, language understanding, robotics, and so on. It's a very different paradigm. There's a real learning going on, and the results are excellent, and the progress is rapid. And computer vision has played an important role in all this because helping other areas. So due to that, there's a dynamic increase in number of papers, number of attendees in conferences, and then data sets, startups, and many professors are moving to industry. There are many software platforms, libraries, like Caffe, Keras, TensorFlow, Chainer, and so on. And also GPUs are becoming very crucial to do this research because the CPU are not powerful enough. And there are many, many online courses, resources, tutorials available, as I mentioned earlier. So the computer vision conferences and journals, we have 3 major conferences: the ICCV, International Conference on Computer Vision and Pattern Recognition, CVPR, and European Conference on Computer Vision. And then journals are PAMI, IEEE Transactional PAM Machine, Pattern Analysis and Machine Intelligence, and International of Computer Vision, and Computer Vision and Image Understanding. So also the machine learning conferences, many computer vision people are publishing papers there. So the most prestigious NIPS. Then we have ICML, International Conference on Machine Learning, and then ICLAIR, International Conference on Learning and Representation. So I was at NIPS last month, and there were so many people wanted to go to the conference, so they opened the registration. Within 12 minutes, it was closed. And they made a joke about that. That's faster than this year's Burning Man, but it's still not as fast as Beyonce's concert, maybe next year. So that is a special phenomenon happening with the deep learning. And this is the CVPR attendance. As you see, 10 years ago we used to have very few. Now it has drastically increased. Now we have 6,000 from 1,000 to 2,000 from 6,000, which is amazing. And same is number of papers. So as I mentioned, deep learning has been disruptive force. Computer vision is impacting other areas like natural language understanding, robotics, computer graphics, audio and speech sketches, AlphaGo, the game playing, and it has really learning. And learning can be done supervised manner or semi-supervised, where you have the ground truth which you want to system to predict, or semi-supervised where you have part of the ground truth, you don't have all, and then weakly supervised that you have the labels at the weak level, like you just have a point or not completely annotations, and unsupervised where you don't have any supervision, and that's the hardest part, and that's probably the most active area. And then there's a self-supervision and reinforcement learning, which is used a lot in robotics. So main themes we are going to discuss in the class will follow that. A lot of work recently in unsupervised learning, reinforcement learning, transfer learning, and domain adaptation. Multimodal analysis, where we can use the audio and video and text, and end-to-end learning complete system, and Bayesian deep learning, and so on. So this is kind of general introduction. Okay, so these are some of our last year's papers published in CVPR, ECCV. And I'm going to quickly go through these to give you an idea what kind of research we are doing and how you relate to the, in general research, computer vision, and some of the work we will be discussing in this class. So this paper was in CVPR about 6 months ago. And by the way, CVPR is the conference which has the highest impact factor in all IEEE conferences. And this relates to the human semantic segmentation for person re-identification. So person re-identification, the idea is that we want to retrieve an image of a person from a large gallery. And so we have a query and gallery images, but they are captured from different cameras. And so this is the cross-camera data association problem. So let's say we have a query image here, and we want to go to the gallery and find the match for this. And this is an incorrect match. These green ones are correct matches. There are lots of people, different views, and so on. And this is the refined version, another method. We get quite a few correct matches. And then this is another version of the method. So these matches are sorted. So this is the first best match, the next best match, and so on. That's called rank. This is a rank 1, and then this is a rank 10. So challenges are that, you know, there can be elimination condition change like this, or there can be different parts of the body parts visible. Suppose your head is not visible because of covered by the umbrella, and posture of person can vary, and background clutter, as you see here, and also occlusions occluded by a tree. So our method uses the semantic segmentation of the body parts, and this is the overall method to find the features given an image of a person. We go through this process to get the feature vector. So it is this first part, we just compute the features using the inception model V3 and get this feature vector of 2048 dimension, and this uses a global average pooling. Then we go through the same image and come up with semantic segmentation of this, and we get these semantic segmentation maps like this. Then we take this multiply these semantic segmentation with these features. We get these features because we have different body parts, the background, upper body, head, and so on. So we will get corresponding to these features, and then we will have one for foreground and one for and then the other body parts. So we have this way global representation features. There's the upper part of the network I showed you. Then we have foreground representation, and then we have body part representation. We have three 2048 dimensional feature vectors, and we will use those. So we did these using these data sets which are benchmark, 3 data sets, and then first, as we say, that we want to use semantic segmentation to help in the re-identification problem, and these are the typical results. Here you see that the shoes, hands, and lower body, upper body of these persons. There's another example here. And so the results using the semantic segmentation applying in the re-identification problem are here. So we have this data set from Hong Kong. So for this query, so this will get you the retrieval of the best matches using only simple features, inception V3. This will give you the features, the retrieval using our method, and as you see, all are correct. And another example is very difficult problem. It give you these matches, but these are wrong. But then we can improve that. We get pretty good results. Another example, again, this is more complicated, so we get some red ones here, and so on. So this one data set, and it's important to show the results on several data sets, otherwise paper don't get accepted. So market data set, again, inception V3. This is our using our semantic segmentation, and this is another example, and so on. Pretty good results. And the Duke data set, same phenomenon that we can get almost all of them correct. So using the different body parts and multiplying those with the inception V3 features helps. So we can look at the quantitative results in this, and these are different metrics, the mean average precision, rank 1 results, rank 5, rank 10. These are the other methods, and these are our method when we combine with semantic parsing, and then without combining semantic parsing, but when you combine the semantic segmentation, we get pretty good results. A big improvement, as you see, with re-ranking. So this is one application of the deep learning for human re-identification problem using the human semantic segmentation. And there's more detail given in this paper, and there's also a video on YouTube. So second problem I want to talk about is the drone videos. We want to detect the objects there. This was also in CVPR. And so idea is here that we have the video taken from drone, where these are the vehicles. There are lots of them, and we want to automatically detect that. So this is a data set from Wright-Patterson Air Force Base, and covers about 19.5 square kilometer. It's about 1 hertz, and there are lots of pixels. The resolution is large, and each pixel is roughly correspond 1/4 meter, and we have many vehicles, so about 2.4 million vehicles in these frames, typically 2,000 in every frame. So we have these 8 area of interest, and so now video frame is large, so therefore we cannot put this in one GPU. So we divide this into these different clips, and then use that to compute, detect the objects, and then we combine. So here is the original video, and these are the vehicles in red, and this is the ground truth. So we need to train the system. So we have ground truth as a point for each of this vehicle. So if you look at this more details, so this is the original image. These are the annotations, the ground truth. So this we can zoom in here like this, And so we compute what is called heat map. Using these points, we apply Gaussian blur, and this becomes like an image now. And that's what we estimate. So this is the video. So we, in order to detect the vehicles in the center frame, we look at the 2 frames before, 2 frames after. So we take the stack of 5 frames, put in this neural network, and these are different layers, and then we estimate the heat map. And these are the different receptive fields at different layers. So we start with 15 by 15, but using this pooling and so on, so receptive field keep increasing and reaches up to 72 by 72. So, and these are the details about the learning. It's a supervised learning. So let me show you some experiments. So in this one, we'll show the ground truth and also what is detected with a circle. And what is missing is these green one we are not able to detect. The results is shown as a precision recall curve, and we compared that with other methods, and we are doing here, so it's a big jump from the current state of art, which is very good. This is another area of interest. Again, we can do a big improvement here. The next one, so again here, from here to here. And so now this is, you can ask, well, you can detect the vehicles using just 1 frame. Why do you want to use 5 frames? But since these objects are very small, so motion really helps because we want to detect moving objects. And so we can improve a lot. This is our method. This is using single frame. So these are the quantitative results. So we can compare with other methods. We can get a very high increase for area of interest 1, 2. Again, you can see we can do pretty good, and this is the average. So that's about the object detection in the video, in the wide area surveillance video. So the next thing I want to talk about how we detect the anomaly in surveillance video. So as you know that there are many cameras, and there are lots of videos, and videos like this, and so nobody actually look at them because there are not enough people. So we want to do some automatic analysis on these videos. So we are interested to detect the anomalies, and for example abuse, arrest, and arson and so on automatically. So now that will signal an activity that deviates from normal patterns. And these anomalous events can be traffic accidents, crimes, or illegal activities, and they rarely occur. So our approach is that we want to detect anomalies by exploiting both normal and anomalous videos. And we will avoid the annotation because it will take a lot of time to avoid the anomalous clips in the training video. So we'll learn these anomalies through deep multiple instance ranking, and we'll leverage the weakly labeled training videos where we'll have long video and we'll say there's somewhere an anomaly, but we don't know where, and there'll be some videos which will have anomaly, which will not have anomaly. So we'll just have these weakly labels. So what we are going to essentially do, we'll learn this function, ranking function f, which will give a high value for the clip, which is the anomalous, and low value for clip, which is normal. And so we'll take the video and divide in these clips, and all these clips in a video will become a bag. So this is an anomalous bag, and this is the normal bag. So we want to learn this function such that any clip in this bag, the function f is higher than any clip in this bag, and that's the ranking function. And we will write this in a loss function like this, that the if we take the maximum of the normal and subtract from the abnormal, and we want to normalize between 0 and 1, so then this and 0 will pick the maximum from that, because we want to get a positive, and that will do our job. So, so the process is we take a video, we divide in these clips, 32 temporal segments, and we will have anomaly video and normal video like this, same process, and we will compute, so this will become a positive bag, and then this will become negative bag, as I explained to you, and we'll compute some features, video features, and we'll have these different fully connected layers, and we will get this output from the different instances for positive bag and negative bag, and using that function as explained to you. So these are the qualitative results. So you see here a video, and this is a function which we are learning. So everything is normal, then all of a sudden some abnormality happen, and this will give you a very high value. So this is another example, and this is a ground truth shown here. And more examples and so on. And this is a normal video, so there's nothing actually happened. So we're playing this video at the high speed, so it may appear abnormal, but it's not abnormal. And these are the quantitative results. So some simple binary classification will not work that well. And this is some other method, and this is third method, and this is our method. So we can do quite much improvement. And our methods are weakly supervised. So that's what about the detect anomaly in surveillance video. So I have one more paper. This was in ECCV. And here we are interested in counting people in a crowd. So we want to estimate number of people, and we want to estimate the density, and also we want to locate the people. So say, given an image here, we want to say how many people are there. So answer is 101. Also, we want to say, you know, the pixel, what's the density, you know, what's the area, there are more people. So there are no people here, there are more people here. And then we want to actually localize this, all these people here, we want to put a dot on that. So this has lots of application, you know, in safety and surveillance, and political significance of the rally, volume of commuters, and counting. So our contribution are that we want to solve these three problems simultaneously: counting, density estimation, and localization. And we also have proposed this largest annotated crowd data set, about 1 million people in these different images. So 1,500 images and 1.2 million annotations. So the challenges are that, you know, there's perspective distortion, and like here there are lots of people, there are few people here. There's occlusion problem. There's dive scene can be very different. And then there's a very low resolution, you know, many thousands of people here. So what we have proposed is that we want to solve this density estimation problem as a side task, and that should help the counting. Because counting you can do just itself, but we have these side tasks. So we start with the coarse estimate of density and iteratively we refine towards the point localization. So therefore we have multiple losses. So this image will be given to deep neural network and then we will get a count. So we'll have loss for the count, we'll get the loss for the density and loss for the localization. So in order to compute density, we take a point as we did earlier in drone videos. We will do the smoothing with the Gaussian with this kernel, and this is the kernel bandwidth, the gamma, which is standard deviation of Gaussian. So given an image like this, we'll compute this multiple level density map. This is a very high Gaussian. Then we decrease and we decrease further, and then this is the actual point localization. So this level we are calling inverse of the standard deviation. So the network is simple. So we take an image here and the density estimate, density ground truth, and we come up with the density estimate different scales, and then also the count here. So we have these losses as I talked about before, and the network has these different layers, and these are training details, typically Adam solver and learning rate and so on. So let me show you some results. So we have the metrics are determined by mean absolute error and mean normalized absolute error and the mean square error, and we get pretty good results. We have the lowest error here, and these are the other methods. So this is our proposed method, but this was our original method a few years ago. So these are some examples. This is a ground truth, 236, and we get 236. Here the ground truth 1612, we get 1610, and here we get 605, ground truth 556, and similarly here. So this was about the crowd counting, the ECCV paper. So I think I'll stop here.